Okay, so here we are going to do now an example of two alkylations followed by hydrolysis and decarboxylation. How about that? Okay, so let's go to a clean page. So let's say that I start with diethyl malonate. There you go, diethyl malonate. Typically, we abbreviate the ethyl by ET. And well, so you have a couple of hydrogen atoms here that they are fairly acidic. So that means that I can abstract one of those hydrogen atoms with a base like sodium ethoxide. Sodium ethoxide. So this grabs a proton and we get a carbon ion there, right? So we can write it down like a CO2 ethyl, CO2 ethyl. And then here now we have a carbon ion. So then now I can react that with an appropriate electrophile, like a methyl iodide, nucleophilic attack, displacement of the halogen, and then now I will have my alkylated diethyl malonate. Notice that we still have one hydrogen atom there, and now I have a methyl group attached to that position. So I can go through a second abstraction of a proton. Again, I can use sodium ethoxide, abstract the proton, get the formation of a carbon ion, and then now we have methyl there, and we have the carbon ion. So then now let's say that just to change things, we use that particular bromide. Huh? Notice that I'm choosing a bromide that is primary, and so displacement of the bromide. And what do you get? Now your product will be CO2 ethyl, CO2 ethyl, and then now I have a methyl attached there, and then a CH2 followed by an isopropyl, right? There you go. So then now hydrolysis. And let's say that I perform the hydrolysis as acid catalyzed hydrolysis. So if I have enough enough acid to hydrolyze this, okay, so I will hydrolyze both esters. And what do you get out of that? So you get, oops, sorry. The same thing there. And then now you will get carboxylic acid from one end, carboxylic acid from the other end. All right, so now we need to go to the step of the decarboxylation. So if you were hydrolyzing in a cold H3O plus, you will get the diacid, and you will not go any farther. But now let's see what happens if I have hydrolysis hydrolysis with heat. So if I do it with heat, this is going to be more interesting, because here you can see you can form a sort of a six-member ring there, right? Six-member ring. So that means that I can have a dance of electrons here. I can have the carbonyl group will capture the proton. With a pair of electrons of that sigma bond, I will form a double bond there. And then I get detached, this portion here, you can see all this portion here is getting detached from the rest. So what do you get there? Well, so you will get HO, CO. Now this is not a carbonyl group anymore, right? So then now we have an OH there, and we have a double bond there, right? Double bond attached to the methyl and to the CH2 isopropyl, right? And all the portion, all this portion here, right? And so that is becoming CO2, right? CO2. And so all that is the CO2 came from the yellow portion there. And then now, here you realize that this is an enol, right? This is an enol, because you have a carbon-carbon double bond and you have an OH attached to that. So you can perform a keto-enol tautomerization. And so here I will say keto-enol tautomerization. And what does it mean? That it means that I'm going to abstract a proton from here. Then I'm going to rearrange my electrons in a different way. And then I'm going to put back that proton in that position there, right? And so look at this. And so I will have HO. And so essentially what I'm doing is this, right? I'm bringing this pair of electrons here, localizing that pair of electrons there, and I'm going to put there my proton, right? So then I will have, now there is no double bond anymore. Now I got back my carbonyl group, and then now you can see that I have the methyl group, the CH2 followed by the isopropyl there, and now we got a proton there, right? There you go. So there you can see that in the overall process, actually very little survived from the original compound, right? And there we can go back to the previous slide, and there you can see that the two ethyls, they were gone in the hydrolysis. Then one of the portions here, then it went as CO2, right? And then, so that means that it's only a couple of carbon atoms, of the original diester survive. And then we have, as newcomers, we have the two groups that we use for the alkylations. We have the methyl group there, and then we have this CH2 isopropyl, right? So that is showing up in the final product, right? Pretty cool reaction, huh? And so that's why I call this the superstar reaction of chapter 22. And then there is another variation to that. Another variation to the same idea is that instead of using the diethyl malonate, you can use a ketoester. But here you will see that the idea is pretty much the same. So I have an ester from the right-hand side, and I have a ketone from the left. But again, you should guess that those hydrogen atoms are fairly acidic. So we can do pretty much the same idea. Let's do it with, let's do it like this. I'm going to put step number 1, sodium ethoxide. So now you know what happens there. And sodium ethoxide will abstract one of those protons. Step number 2, I will perform the reaction with benzyl bromide. So that is a primary bromide. So there should be no much of a problem for getting displacement of that. So what will be my final product, my intermediate, if you will? So I will get exactly the same. And I will have attached to that central carbon atom, I will have my benzyl group, right? There you go. So and then now, when you perform the hydrolysis, and let's say that I perform the hydrolysis and heat, what is going to happen? Well, only one of them will hydrolyze, right? This one can hydrolyze. The other guy here on the left, that is not an ester, that is a ketone. So that carbonyl group will survive all the way to the very end, right? It'll survive all the way to the very end. So that means that in the final product, I will get this, right? So let's say that I don't go through a second alkylation. I'm just content with performing one alkylation. And so I will get that group attached, and then this portion here will be gone as CO2, right? So that will be my very final product. All right, so what is the lesson out of this? So you may want to remember some pattern in this kind of reactions. And the pattern is this, that when you are using a diester, when you use a diester as a starting material, see, I have one ester here, one ester there. The final product that I will get after going through the decarboxylation and everything, you will get one carboxylic acid here, right? So there will still be a carboxylic acid in the final product. And you get, of course, the two alkyl groups that you attach there, right? How about when you use the acetoacetic ester? Acetoacetic, because you have an acetyl group there. Acetoacetic ester. There you can see, you start with an acetyl group there, and it is still there in the final product, right? So that is very, very useful to recognize that pattern, because then now in the future, when they give you a target product, they tell you, how can you synthesize this? What will be the appropriate starting material to synthesize this? And so then you can judge on what should be the starting material based on the presence of an acetyl group. If you have an acetyl group, the starting material should have been the ketoester, right? This is the ketoester. The ketoester, that in particular is ethyl acetoacetate. That will be the name of that compound. But if you have a carboxylic acid in your final product, like here, you have a carboxylic acid here, and so then you say automatically, you will say, my starting material should have been the diethyl malonate or dimethyl malonate. So it doesn't really matter if it is ethyl or methyl. In both cases, you will get the same result, right? Now, there are even some fancier things that you can do because it depends on the kind of alkyl halide that you use. You can even form some cyclic products. If you have a dibromide, for instance, and if you perform a double alkylation, think about. So if I use a dibromide like this, well, so that means that my initial diester, it will get attached to this carbon atom and it will get attached to that carbon atom. So and it's in that way that you are making a ring, right? So there you go. So we stop here.